Okay, today I'm going to go through a video to summarize the answers to quiz 2 for chemistry. And I went ahead and wrote this out in advance because I didn't want to make any mistakes going along. So we look at, one thing I will say, if you didn't do well on this, this is probably the most difficult concept to grasp that you'll have all year. And so you need to think about it, look at the answered questions and understand that if you have trouble picking it up, if you do some extra problems, it might help. That said, let's look at this first problem. And the first problem is, what is the hydroxide ion concentration in a solution that's made up of 0.2550 molar ammonia and 0.3750 molar ammonium nitrate? And the equation here, it shows the basic formation. Actually, down here we're going to look at the acid, but the basic formation, and the Ka, or the Ke for the base, is 1.8 times 10 to the minus 5. And so you have ammonia plus water forms the ammonium ion plus, in this case, nitrate, but it doesn't really matter, plus hydroxide. So here we have the equation. The Kb here is 1.8 times 10 to the minus 5, and that represents the concentration of the products multiplied together, divided by the concentration of the reactant, not counting water, of course. So that Kb is equal to the number 1.8 times 10 to the minus 5. And you're told that the initial concentration for ammonium ion is 0.3750. The initial concentration for the ammonia is 0.2550, and actually the initial concentration here is 0. Then, so you put your ice table, you write your initial concentrations, and then you assume that you form X amount of hydroxide ion, which means you're also forming X amount of ammonium ion, and you're taking away X amount of ammonia. So in the equilibrium, you have these concentrations. And you put these concentrations in here. So for the reactant, you put ammonia, which is this, and here's the ammonium ion, and here's the hydroxide ion. And at this point, you make the assumption that X is significantly smaller than the initial concentrations that you're given. Now, someone asked me, well, how do you know that's true? Well, what you do is you assume that that's true, and then after you get the answer, you check it by showing that it's less than 5% of the initial concentrations. So you make the assumption, you work out the answer, and when you make the assumption, these x's fall out, and you end up with this equation, and you solve this equation for x, and you get 1.22 times 10 to the minus 5. Now, if you take, that is actually like, compared to the initial concentrations here, that's like 0.001% of these. And so it's well less than 5%. So that tells you your assumption was okay. So here's the answer to the first problem. 1.22 times 10 to the minus 5. And if you went ahead and calculated a pOH, the pOH here would be 4.9. But I didn't ask for that. Now let's move on to the second problem. A buffer is made by adding 0.2 moles of NH4Br and 0.075 moles of ammonia to a sufficient amount of water to make 1 liter. Okay, so it's telling you the molarity here is this many moles per liter and this many moles per liter. So it's telling you the concentrations in the problem like that. Now, we're talking about the formation of an acid, so it's exactly the opposite of this equation up here. They're giving you a Ka, so you want to work with to form an acid, which is this equation, or the reverse of this equation. So then you write it like this. That means the Ka, which is given as 5.6 times 10 to the minus 10, and that is equal to the concentration of the products, which are these two, divided by the concentration of ammonia. You then set up your ice table. Your initial concentration is 0.2 of ammonium ion, and 0.075 of ammonia, and no acid or no hydronium ion. You're going to form X hydronium ion, which means you're also going to form X of the ammonia, and take away X from the reactants. So these are your final concentrations. Here, you add X on this side and you subtract X from here, and then you put that in this equation here. Again, you make the same assumption, and you're going to check that in the end, and you end up with this equation. And if you solve this equation, you get 1.49 times 10 to the minus 9, and obviously that's less than 5% of either of these two numbers. So your assumption is okay. If you calculate a pH for this by taking the negative log base 10 of this number, you get a pH of 8.8. So pretty much the same as what we did above here. It's just that we're going in the opposite direction and have a Ka instead of a Kb. Now, the second part of this question is, let's say you add 0.15 moles of hydrochloric acid. Now, I didn't mention a volume. Therefore, you just assume that there was no change in volume. If I'd have mentioned a volume, you would have to take that into account. It actually makes the problem easier. So when you add 0.15 moles of hydrochloric acid, which is the same as adding that many moles of hydronium ion, in this reaction up here, it will react with this and move from the right to the left. So you take away from ammonia and you form more ammonium ion. And so you add that amount to the ammonium ion, so you end up with this amount of ammonium, and you take that amount away from the ammonia, so you end up with this amount. And now this is in a liter, and so you end up with these concentrations. Now, with these concentrations, you plug that into the ice formula. You have this initial concentration for ammonium, this initial concentration now for hydronium ion, because it's all of the added acid has been consumed, and this concentration for the ammonia. You have the formation of X on the product side and the reduction of X here, so you end up at equilibrium with these concentrations. You put these numbers into the same equation, make the same assumption about X here, and solving for X, you get 2 times 10 to the minus 9, which again is obviously less than 5% of either of these two numbers. The pH here is 8.7. Now, what this is supposed to show you is, despite the addition of a pretty meaningful, if you just added this to water, a liter of water, so that it was 0.15 molar hydronium, if you just added that to water, 0.15, the pH of that would be about 1.82. And yet you add it here, and it only changes the pH 0.1 points. So that's the whole idea behind buffers, is by having these kinds of solutions set up in the way they're set up, you can add a meaningful amount of acid and get very, very small changes in pH. If you have any questions about these two problems, please let me know.